When you look at your code, it appears to run in order. One instruction follows the next. One line executes after the previous line. The logic feels sequential and predictable. But inside a modern CPU, that is not always what happens. Under the surface, the processor may execute instructions in a different order than they appear in your program. And yet, the final result is still correct. That mechanism is called out-of-order execution. In this video, we're going to explain what out-of-order execution is, why it exists, how it works at a high level, how it relates to pipelines and branch prediction, and why it is one of the most important performance techniques in modern processors. Let's begin with the problem it solves. In the previous video, we explained pipelines. A pipeline overlaps instruction stages to improve throughput. Multiple instructions are in different stages at the same time. But pipelines have a weakness. They stall when instructions depend on each other. Imagine this simple sequence. Instruction A loads a value from memory. Instruction B adds something to that value. Instruction C multiplies a completely unrelated value. If instruction A must wait for memory, which is slow, then instruction B must also wait because it depends on A. In a simple in-order processor, instruction C would also wait, even though it is completely independent. Why? Because the processor executes instructions strictly in program order. So if instruction A stalls, everything behind it stalls. This wastes cycles. Out-of-order execution exists to avoid that waste. Instead of waiting for instruction A to finish before doing anything else, the CPU looks ahead. If instruction C is independent, meaning it does not depend on the result of A, the processor can execute C first, even though C appears later in the program. That is the core idea. Execute instructions as soon as their inputs are ready, not strictly in program order. But there is an important rule. Even though execution may happen out of order internally, the final results must appear as if the program executed in order. The observable behavior must remain correct. So how does a CPU do this safely? Modern processors use a structure often described in three main phases. Fetch and decode instructions in order. Issue instructions to execution units when their operands are ready. Commit results in order. That last part is critical. Results are committed, meaning made architecturally visible, in program order. So even if instruction C executes before instruction A internally, the processor will not commit C's result until all earlier instructions have safely completed. This preserves correctness. Now let's talk about what makes this possible. Out-of-order processors use several internal structures. One of the most important is the instruction window. This is a buffer that holds multiple decoded instructions waiting to execute. Instead of immediately executing the next instruction, the processor collects a group of instructions and analyzes their dependencies. If an instruction's input operands are ready, it can be sent to an available execution unit. If it depends on something that hasn't finished yet, it waits. This allows the processor to find independent work and keep the pipeline busy. Another important concept is register renaming. At first glance, dependencies appear everywhere in code. For example, instruction A writes to register R1. Instruction B writes to register R1 later. Even if they are logically independent, they appear to conflict because they use the same register. Register renaming solves this. Internally, the processor maps architectural registers, like R1, to physical registers. So instruction A might write to physical register P5, instruction B might write to P9, even though both refer to R1 at the program level. This eliminates false dependencies and allows more instructions to execute in parallel. Now let's connect this to pipelines. In a simple pipelined processor without out-of-order execution, a stall in one instruction blocks everything behind it. In an out-of-order processor, the pipeline can remain busy because independent instructions move forward. The processor dynamically schedules work to keep execution units active. This dramatically improves throughput. Now consider memory operations. Loads from memory can be slow, especially if they miss the cache. In an in-order design, a slow memory load can stall the entire pipeline. In an out-of-order design, while the load waits for memory, Other independent arithmetic instructions can execute. The CPU hides latency by doing useful work during waiting periods. That is one of the main performance advantages of out-of-order execution. Now let's clarify something important. Out-of-order execution does not violate the logical structure of your program. From your perspective as a developer, the code still behaves as if it ran sequentially. This is guaranteed by in-order commit. Internally, execution may be rearranged, but externally visible effects, like writing to memory or updating registers, occur in the correct order. Now, let's address hazards. Earlier, we discussed data hazards in pipelines. Out-of-order execution is essentially a hardware solution to many data hazards. By tracking dependencies precisely, the CPU can allow safe reordering while preventing incorrect behavior. But this requires complex bookkeeping. The processor must track which instructions are waiting on which operands, which execution units are free, which results are speculative, which instructions are safe to commit. This is why out-of-order processors are significantly more complex than simple in-order designs. Now let's connect this to branch prediction. When a branch is predicted, the CPU may speculatively fetch and decode instructions beyond the branch. Out-of-order execution allows those speculative instructions to execute early. If the branch prediction was correct, performance improves. If it was wrong, the processor must discard speculative results. So out-of-order execution and speculative execution work together. Prediction guesses the path. Out-of-order execution keeps the machine busy along that path. Now let's consider performance implications. Out-of-order execution increases instruction-level parallelism. That means multiple independent instructions can be in flight and executed simultaneously across different functional units. Modern CPUs often have multiple arithmetic units, load/store units, and vector units. Out-of-order scheduling ensures those units are kept busy whenever possible. Without it, many of those units would sit idle while waiting for dependent instructions to complete. Now let's address a misconception. Some people think out-of-order execution means the CPU randomly reorders instructions. It does not. Reordering is constrained by data dependencies and correctness rules. The processor cannot violate true dependencies. If instruction B needs the result of instruction A, B must wait. But if two instructions are independent, their order does not matter for correctness. The processor is free to execute them in whichever order maximizes efficiency. Another misconception is that out-of-order execution guarantees maximum performance. It improves average throughput, but it cannot eliminate all bottlenecks. Cache misses, branch mispredictions, and memory bandwidth limitations still matter. Now let's connect everything in the series. Instruction dispatch determines which instruction is next. Branch prediction guesses control flow to avoid stalls. Pipelines overlap instruction stages. Out-of-order execution rearranges independent instructions to keep pipelines full. Together, these mechanisms allow modern processors to execute billions of instructions per second efficiently. If you remove out-of-order execution from a high-performance CPU, performance would drop dramatically, especially for complex workloads with many dependencies and memory accesses. Out-of-order execution is one of the core reasons modern processors can tolerate latency and maintain high throughput. At a deeper level, this technique shows something important about computing. Software appears sequential. Hardware is massively parallel. Out-of-order execution is one of the bridges between those two worlds. It allows sequential programs to benefit from parallel hardware resources without requiring the programmer to explicitly manage instruction scheduling. And that is a remarkable engineering achievement. In the next step of this series, we could explore superscalar execution, how multiple instructions are issued per cycle, or dive into CPU caches and memory hierarchy, which introduce another layer of performance complexity. But for now, you can summarize out-of-order execution like this. The CPU executes instructions as soon as their inputs are ready, not strictly in program order, while committing results in order to preserve correctness. That balance between flexibility and correctness is what makes modern processors so powerful, and it is another essential piece of the software execution model.